It's like we got people
Well,
from
let's
all
go ahead
around.
and get started here. So hello, everyone, and welcome to the October NASA Night Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to bring this webinar to you with Dr. Robert Zellem from NASA's Jet Propulsion Laboratory. Welcome to everyone joining us on the YouTube live stream. We're very happy to have you with us. These webinars are monthly events for members of the NASA Night Sky Network. And we look forward to continuing to live stream. This has turned out to be a very popular thing. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, check the links in the chat. I'll put those in just a moment. Before we introduce Rob, here's Dave Prosper with just a couple of announcements.
Hi, everyone. Yep, just going to keep it quick here. Just heard briefly early this morning that our Sky and Telescope magazine subscription discount link is invalid, and that is okay because I just sent an email to their service, so don't worry. We'll have our discounts back very soon. They've been changing hands and stuff, so it's all good. We'll get it worked out. They're very quick. So the other thing is very big. The Outreach Award pins have arrived. They are very pretty, very nice, and they are ready to order. Due to the ongoing pandemic, our qualifications for ordering are a little lower than in previous years. This year, we know a lot of events are still canceled or delayed, so we just need you to report on 2 events throughout the year. Now, if you've been reporting on a couple events every quarter, you're set. And if you've been reporting on more than a couple events every quarter, that's fantastic because we love the more reports that you add to your events. That's great. But yeah, it is not too late. And yeah, the order period is through March of next year, I think. I got to double check because we changed it a little bit. There's more details coming up. I'm sending out a formal announcement to coordinators in a couple of days. And we will, it's also been in the newsletter and it'll be in it again in about next week, actually. And if you want to know the details right now, it is at bit.ly/NSNpins2021. And that is going in the chat as well. And that's the biggest order. That's the biggest thing. Oh, one more thing. If you, we are hoping to give some folks prizes for putting on scheduling their events for next year. So if you're putting your events onto the Night Sky Network calendar for 2022 or thinking maybe you should start, you should definitely start. We're probably going to have a cutoff around the beginning of the year. Grab all the events, do the randomizer, so you get some fun prizes. We think we're gonna have details about that shortly, but it'll have a little grab bag of fun outreach materials as well. And that's it for me. Back to you.
All right, thanks. I also, and Vivian might have something to say here too. I want to thank everyone for filling out the survey that we've been asking you to do for the past month or so. Vivian, any words of about that?
Just a big thanks to the maybe about 30 or 40 participants in the focus groups that we've had for the past week and a half. And those are going to all get analyzed, and we're going to have the report definitely by the end of the year, probably by the end of November. So we'll put that in the newsletter too. So keep an eye out. Thanks everybody who filled it out and joined us.
All right, thanks. For those of you on Zoom, you can find the chat window and the Q&A window if you look at your Zoom menu bar. Please feel free to greet each other in the chat window, making sure that you go down to the bottom and select everyone. If you do something else, it'll just come to the host and the panelists. If you have any technical difficulties, you can put that in the chat, or you can send us an email at nightskyinfo@astrosociety.org. If you have a question for Dr. Zellem tonight, please put it into the Q&A window. That will really help us keep track and know if we've answered your questions or not. We also have a lot of times there's multiple people asking the same question, and so that way we can kind of lump questions together too. Again, I want to say welcome to the October webinar of the NASA Night Sky Network. This month we welcome Dr. Robert Zellem to our webinar. Rob is a scientist at NASA's Jet Propulsion Laboratory, working on ground and space-based observations of the atmospheres of exoplanets, planets outside of our solar system. I think that's really exciting that we can actually see, and examine the atmospheres of these distant planets. He's observed and worked at major observatories and is involved with developing simulations to predict the ability of NASA and ESA exoplanet dedicated missions to measure these exoplanet atmospheres. Rob is also active in leading citizen science projects to help aid in the characterization of exoplanets. And so later on, he'll tell us a little bit about how you can get involved with helping with this effort. So please welcome Dr. Robert Zellem.
Everyone, thank you so much for having me. And thank you, Brian, for that awesome intro and making me sound a lot smarter than I actually am. I really appreciate that. All right, so my name is Rob, as I said, and today I'll be talking about exoplanets and ultimately finding life in the galaxy. I'm a giant nerd. I love space and I want to find aliens because I love Star Wars and I want to ride the Millennium Falcon. But in order to do so, I have to find, or scientists have to find, potential places where the Falcon could be docked. So as was said in my intro, I work at NASA's Jet Propulsion Laboratory operated by the California Institute of Technology. My building, which I haven't been in about a few years, is actually right down here. And this photo was clearly taken thousands of years ago when LA actually had water and snow in it. As I mentioned before, I've always loved space and astronomy. This is actually little Rob at the Kennedy Space Center meeting one of his heroes, an astronaut. Sometimes people ask me if I've ever wanted to be an astronaut growing up as a kid. And my answer is a very firm and hard no. I am definitely afraid of heights. So that's kind of a job requirement, is to not be afraid of heights to be an astronaut. So I do what I think is the next best thing, and I'm an exoplanet astronomer. So what does this mean? Let's quickly unpack this. Well, exoplanet, that's just simply short for extrasolar planet. Extrasolar means anything beyond the solar system, outside of the solar system, where planet obviously equals planet. So if we cram them together, exoplanet is any planet outside of our own solar system. And I'm an astronomer. If you don't know what that is, you're probably in the wrong talk, but as you are all aware, that's someone who stares at the sky, or more likely in my case, their computer for way too long. And I work at NASA's Jet Propulsion Laboratory working on exoplanets, trying to characterize them to figure out what contents are in their atmosphere, working on missions, instruments, both on ground and in space. And ultimately, I'm working towards helping answer that question. That ultimate question is, are we all alone in the universe? Or is there life elsewhere out there? So I should say really quickly, I am married to a historian, and if I do not show this next slide, she'll bust into this room and kick me off of Zoom. So it's always also helpful to look back from where we came to see where we're going. So even though exoplanet science is one of the newest fields in astronomy, it's only about 20 to 30 years old, depending on how you count. The idea about exoplanets, about planets outside of our galaxy, our own solar system, is not a new idea. This has been around for hundreds of years. So for example, Giordano Bruno, that 16th century philosopher who looks a lot like Emperor Palpatine up there on the right, actually postulated the existence of exoplanets. And Isaac Newton, as you are all aware, he invented the fig Newtons. He said in his work Principia, where he actually discussed the theory of gravity, he also said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, we have 8 planets in our solar system, 8 because Pluto is not a planet. We have 8 planets in our solar system orbiting around the sun. And it stands to reason that when we go out into the night sky, and you look up at all those points in the sky, all those stars, that they have planets orbiting around them as well. And we know that these 2 dead dudes are absolutely correct now, hundreds of years later. As our technology got better, as we learned how to look, where to look, when to look, we have started discovering exoplanets and at an ever increasing rate as well. So we now know that planets are ubiquitous, they're everywhere. And thanks to some NASA missions, we now know that there are at least as many planets as there are stars in the sky. So this is all well and good. We're discovering tons of exoplanets. We've actually discovered over 4,000 as of today. But we want to find life, right? We want to find aliens and determine if, human life or life on the Earth is something common or if it's something unique. And to do that, we sort of have this sort of three-step method that I boiled down here. First, you have to find the exoplanet. Then you can determine if it can support life. Then you actually have to find the life itself. So let's look at the first step. How do we find exoplanets? Well, there's actually a problem. It's really difficult to see exoplanets. They're so very far away. We typically only see the star that it's orbiting because the star is so much brighter than the planet. The planet is so much dimmer. So we either need to block out the star to block out its light and see the small planet orbiting around it, or we need to use other methods to infer that the planet is there. So there's actually a variety of methods that we use to find exoplanets. The three I'll be focusing on tonight are radial velocity, transit, and direct imaging. These are arguably three of the methods that have given us the most information about exoplanets, at least the radial velocity and transit methods. And then I work personally also on direct imaging methods. So I have to, I'm contractually obligated to say that or my funders will get mad. So let's look first at the radial velocity method. Well, the radial velocity method is sometimes called the Doppler shift or wobble method. When you have a planet orbiting around the star will gravitationally tug on the planet and cause the planet to orbit it. But the planet also exerts its own gravity on the star. And if the planet is big enough or close enough, it'll cause the star to wobble back and forth. And as the star wobbles towards us, its light gets blue shifted. Its light gets compressed. It's a lot like Doppler shifting. It is Doppler shifting. So if you're ever walking down the street in an ambulance or a very loud car passes you, these sound waves are actually compressed, which increases the pitch and the frequency of that sound. The same thing happens with light. As that light comes towards us, the wavefronts are compressed and the light is shifted towards bluer wavelengths. Then when the star goes away from us, those light waves are stretched out effectively. The waves are increased and the light is shifted towards red wavelengths. And this gives us the mass of the planet. The bigger the planet orbiting around the star, the more gravity, the more it tugs and wobbles its star back and forth. The other method that we can use is called the transit method. The transit method is when you're detecting when a planet passes in front of a star. So we're observing these host stars. We might get lucky and a planet might occasionally pass in front of its star, block out the star's light, and effectively cast a shadow all the way back on the Earth. And transits are extremely helpful and important because they allow us to directly measure how big that planet is relative to its host star. The bigger the planet, the more light it blocks out, the bigger the dip in brightness of the host star. But at best, this dip in brightness is typically on the order of about 1%. This method, as I'll talk about later, also allows us to study the atmospheres of these planets by observing how the planet's atmosphere blocks out and absorbs light from its host star. And this method has been used very successfully. It's been used to discover about 3,000 of the 4,000 currently known exoplanets. So transits, it's actually relatively cheap to observe them. As I'll talk a little bit later, you can use telescopes as small as like something that's 4 or 6 inches. I've also saw a post occasionally online a few years ago where someone used a single DSLR camera on a barn door tracker to observe a transiting exoplanet. So no telescope at all. And again, it gives you the planet size. There are disadvantages though. You're biased towards large planets in short period orbits. You're biased towards planets that are larger, that block out more light, and therefore have a larger signal, but there's also false detections as well. And you have to have that geometry, just like radial velocity. The planet has to be orbiting in this plane, so it blocks out the star relative to your line of sight. If it's orbiting perpendicularly, you won't see any transit and you won't see any planet detection at all. So I mentioned before that the transit method has been used successfully to discover about 3,000 of the 4,000 known exoplanets. And that's thanks to ground-based surveys and space-based surveys, one of which was NASA's Kepler mission that discovered a few thousand. And now there's a mission that was launched just a few years ago called NASA's TESS mission. TESS is doing a full sky survey over the next few years. And TESS is predicted to discover potentially up to 10,000 new exoplanets. So today we know of 4. TESS might discover an additional 10. And the reason that it's important to discover new planets is because the transit method is used repeatedly and routinely by space telescopes and ground-based telescopes, one of which is the Hubble Space Telescope, which has looked at tens of planets. James Webb, when that launches, hopefully next in December, that will be observing hopefully tens to hundreds of planets. Ariel, a European Space Agency mission that'll be launching within the next decade, is dedicated to exoplanet science and will be observing hundreds to 1,000 planets. And then Astro 2020, these are the next flagship missions that NASA is considering right now that we'll actually potentially be hearing about as soon as next week or the week after. Those spacecraft are likely going to be using the transit method as well to actually search for signs of life. So we've been routinely using the transit method to look at and characterize the atmospheres of these planets. And it's likely that we will continue to do so for at least the foreseeable future. But in order to observe a transit with these space telescopes or even any ground-based observatory, we have to know very precisely when that transit will occur. So let's pretend I write a Hubble proposal to observe an exoplanet. And I look up online and I determine that that planet will be observing or transiting its host star. And I estimate that it will transit its host star in this red dashed line. But let's say that that planet has some uncertainty with regards to its timing. That planet could actually transit its star a little bit earlier than I anticipate. And there's 2 ways to get around this. One is by building additional buffer to our observing campaign to ensure that we don't miss the transit. But that's not really using this time very efficiently on that telescope. You know, if I had to build in an extra 10 or 15 minutes to my Hubble proposal or my James Webb proposal, while it doesn't sound like a lot of time, if you do the math, it's really costly. And that's also an additional science that you could have been doing on other cool science cases as well. So there's really this need on some of these targets to update their mid-transit times, to update their parameters, so you can more accurately predict when the next transit will occur, and you can use these very, very precious resources a lot more efficiently. So that got us thinking, well, why don't we use small telescopes to do this? We're working a lot with a group called the MicroObservatory out at Harvard CFA. And they are routinely getting data from the robotic 6-inch telescopes, both in Tucson and in Massachusetts, to observe transiting exoplanets. And we were just quite honestly blown away by the data quality. These are 6-inch telescopes, they're robotic. Their pointing is not perfect. The target slews by hundreds of pixels across the frame. It observes any given night. This is an example, transit light curve I'm showing on the right. It's actually a relatively dim star, about 11th magnitude. And despite all those issues and those confounding variables, we're actually able to get a really, really nice looking and science grade light curve. And I can say it's science grade because they actually published this in PASP in 2020. So that got us thinking is that if a single 6-inch telescope could really make these high precision measurements, what does that mean about other folks out there that have their own telescopes that can actually really contribute to NASA science and goals in a very meaningful way? So that led us to launch a project called Exoplanet Watch, which is where citizen scientists monitor transiting exoplanets. So Exoplanet Watch is a campaign aimed at these citizen scientists to routinely observe some high priority targets. This is a collaborative effort to complement existing surveys. So for example, there's basically a European version of us called Exoclock that has been set up to help the Ariel mission, and we have an open collaboration with them. All of our data will be immediately public to the entire community. There's no embargo phase. So as soon as the data is processed on our end, we immediately push that up to our website. There's an opportunity for community feedback and target requests. We're actually getting requests by professional astronomers right now, even though we have yet to officially launch to professional astronomers. We actually have 2 observing campaigns coming up, one in November and also one in December. And the one in December is actually to directly help out a James Webb proposal observing run that'll be happening the next year. So if you're interested in actually directly helping out NASA missions and goals, you can help us observe these targets and use these resources a lot more efficiently. What I'm really excited about as well is that we're requiring observers to be listed as co-authors on any published results. If you do the work, you deserve the credit. And I just want to give a big shout out to NASA's Universal Learning that's funding this entire process. Universal Learning is this really great organization that's funded through NASA that does various public outreach events and products as well, from videos to talks like this. So our goals for Exoplanet Watch, we have an educational goal to engage the public in exoplanet citizen science, increase their confidence about their ability to do science. And then we also have, those boring old typical science goals, like, efficiently using NASA resources so Rob doesn't get yelled at by NASA and fired from his job that he loves. So those are all good things to do. So I'll quickly just go through the user experience. First, you plan your observations. We advertise on our website priority targets for each US time zone, since we are a US funded endeavor. But you can use whatever transiting planning tool you want, such as the Swarthmore Transit Finder or the NASA Exoplanet Archive. Ultimately, you can observe any transiting planet you want. It doesn't matter. We'll take any data you can get, even if it's not one of our priority targets. You then observe your own transits with your own equipment. So you go out in your backyard or you dial up your robotic telescope and you do your own observations. We're also working towards, by the end of next calendar year, opening it up even further so that users who do not have access to their own telescopes or don't live in dark sky conditions or even clear sky locations can actually get some data that we'll procure through robotic telescopes, such as the MicroObservatory. And we'll be launching that by the end of next calendar year. You then reduce or analyze your own observations. We have our own data reduction tool called Exotic that I'll be talking about a little bit later. But you can use whatever you want. I know a lot of folks really love AstroImage J. You can use that for sure. You can also use any sort of homegrown data reduction tool. As long as the file is in the correct format for uploading to the American Association of Variable Star Research Observers website, that's all that matters at the end of the day. We're really grateful for our partnership with the AAVSO. They have their own exoplanet data database they're letting us use and our users use for free. And it's been a really great process so far. Then once you upload your data, you just sort of sit back and relax and hopefully get published as a co-author. Alternatively, you can use any of our data products on our website that are immediately and publicly available to write your own research papers as well. The only thing we ask in return is if you use someone's data and it hasn't been published before, you ask them to be a co-author on your paper, or at least you offer them to be, and then you include some acknowledgement and cite one of our papers as well. Pretty easy peasy. Then on the back end, here at JPL, we have these two servers that routinely scrape the AAVSO pipeline database. And it does this right now about twice a week. We're gearing up for nightly scrapes. Then we reprocess the data. This is to make sure that if any of the values get updated, we can have the latest measurements on our end as well. And then we immediately publish them to our website. We have no proprietary phase. So I mentioned Exotic. This is our exoplanet transit interpretation code. This is a complete analysis software that can run on your own computer. It runs on Windows, Macs, and Linux boxes, so basically anything. And it has a really nice GUI, and it can take your raw image files, your raw FITS files, and it can fully analyze, extract the flux, do the calibrations, do the model fitting as well in as little as about 5 minutes. As far as I'm aware, this is the fastest data reduction tool on the market, and it's free. And it also does these really nice light curve fits that are fully statistical model fits that we actually use to publish. Another cool feature about Exotic is it produces these real-time light curves. This is actually based upon some code that we use at Palomar Observatory, for example, that shows you the transit happening in real time. We use it because we want to make sure we're observing the right part of the sky and not wasting Palomar time. But also, if you wanted to, when we can have star parties again, hopefully soon, you can also use Exotic to show a transit light curve in real time. When you're observing a transit, they're kind of boring. And if they're boring, that's great. That means nothing bad is happening. You're observing a star. You're trying to watch that star dim by 1% over a few hours. And that's kind of hard to see by eye. It just looks like a static field. But if you have this real-time plotter set up of Exotic, you can point to your monitor while people are going by at star parties and say, hey, look, we're actually observing this exoplanet hundreds of light years away right now, and it's casting a little shadow on the Earth. So that's Exoplanet Watch. Oh, We actually launched about 3 months ago to amateur astronomers, sorry for the typo, and we're now launching soon, hopefully within the next 2 to 3 weeks, to professional astronomers. You can contact us by emailing us at exoplanetwatch@jpl.nasa.gov. You can also visit our website down there below, or simply just Google NASA Exoplanet Watch, and hopefully we're one of the top results. All right, I'll get off my soapbox there and get back to the science. So I was talking about how we find exoplanets. So we have the radial velocity method, gives us the mass of the planet. You also have the transit method, gives us the size of the planet. There's also this third method called direct imaging method. And as you've probably figured out by its name, direct imaging purely means taking photographs of exoplanets. However, as I alluded to earlier, this is really difficult. And there's a really big problem with this, is that the planet's light that it reflects or emits is really dwarfed by its host star. So let's think a thought experiment. Let's take a large planet, like a Jupiter-sized planet. Let's also get this planet when it was recently formed. So it still has a lot of heat left over from its formation. So it's big and bright and emitting a lot of light. We take that Jupiter-sized planet and put it around a sun-like star. That's like looking for the light of a firefly flying around a lighthouse, and you're observing it from the other side of the country, because that planet is 1,000,000 times fainter than its star. Now, what about for an Earth-sized planet, or an Earth-like planet? That's the ultimate goal here, is to start characterizing and finding planets that could have life on their surface. Well, that planet is going to be 10 billion times fainter than its own star. That's like looking for one bioluminescent alga around that same lighthouse. So how do you block out the star without blocking out the planet? And how do you block out the star so you can see the planet's light at all? Well, that's where direct imaging comes into play. Direct imaging is literally blocking out that light of that host star using something called a coronagraph. Block out the light from the star and allows you to resolve the light from the planet next to it. It's a lot like during that solar eclipse that we had a few years ago, where instead of the moon passing in front of the sun, allowing you to see the corona or the stars around the sun, you actually use a piece of hardware called a coronagraph to block out the star's light and allows you to resolve the planet's light as well. So I have this handy video to help describe this method. Let me check my audio settings. Okay, I should be good to go. And I can take a sip of water, break too.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. Jwst doesn't block the star's light with an opaque disk as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear, while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects the distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, Jwst will provide the first look at individual planets in star systems that might be similar to our own.
So we'll be coming back to Jwst, now called the Nancy Grace Roman Space Telescope, in a few moments. But hopefully everyone got how coronagraphs work in space and how they work at all. There'll be a pop quiz on this later. So the answer, though, is magic. It all works by magic. In all seriousness, it's a combination of hardware that is able to block out the light from the host star, as well as any internal aberrations or internal reflections in the instrument itself. And then there's also really cool post-processing techniques, software techniques that people use to further increase the fidelity of the data. So direct imaging has been used very successfully for many years, including on the ground here on the Earth. Here's actually some exact direct imaging data taken from, I believe, one of the Gemini telescopes by Jason Wong. Here at the center is actually the black coronagraph that has blocked out the light of the central star. And each of these 4 points of light right here are actually 4 little exoplanets. And as you can see, they're orbiting around this star. So this data was taken over about 7 years. So we're actually looking at an extrasolar solar system orbiting around its host star in real time. And this is just mind-blowing to me that we're able to observe these planets orbiting around this star. Okay, so now what? Well, we have discovered over 4,000 exoplanets, but that's all well and good. We can detect planets, who cares? You know, what we really want to do is we want to take that next step. How do we make the leap from, or the next step from planet detection to now planet characterization? We want to know what these planets are made out of. Are they water worlds? Are they gas giants? Are they terrestrial planets that could have an atmosphere that could support life? But to answer that question first, we have to figure out, does a planet even have an atmosphere? And if so, if it does have an atmosphere, what molecules are present in that atmosphere? And if it has molecules in its atmosphere, could it actually support life? If so, then does it have life? So this takes us to our next step, is we have to determine if a planet can support life. So one of the metrics that's usually used to talk about this is the habitable zone, also called the Goldilocks zone. And this is the zone in an orbit of a planet where liquid water can survive on a planet's surface. It's basically the distance between a planet and the star. The planet's not too close, it's not too hot where water boils off. It's not too far away, it's not too cold where water freezes out. It's at a temperate location. It's where the temperature of these planets is just right for liquid water to survive on its surface. And this is very important because life as we know it requires liquid water to survive. So if we take a top-down view of our own solar system with the sun, Mercury and Venus are a little bit too close, a little bit too hot. Mars is a little bit too far away, a little bit too cold, but the Earth is in that Goldilocks zone. It's not too hot, it's not too cold, it's just right for water to survive and life to survive on its surface. So that gives us sort of a range that we can vet on basically, you know, should we look at planet A or planet B? And we can sort of use this definition of a habitable zone to whittle down our planet list to prioritize what targets we want to look at. But ultimately, what we want to do is you want to determine what molecules are in the planet's atmospheres. Does it have water, methane, carbon dioxide, carbon monoxide? Well, to do that, we actually use something called, believe it or not, Beer's Law. So let's look quickly into Beer's Law. I have a quick, nice little definition that describes and explains it here. That is studying for a test or doing homework while Beer is involved, making difficult classes such as physical chemistry more bearable. That's a great definition. It's actually the definition I routinely use as a graduate student at the University of Arizona to help me get through classes. But the one I'm actually more so thinking about is this. Beer's Law describes how light is affected, how it's absorbed and scattered in and out of a beam. So let's take a chamber of gas and let's fill it full of like carbon dioxide or water or something like that. If we put a light bulb behind that chamber of gas and we look at it on the other side, we expect that light to be a little bit dimmer. And that's because the light from the light bulb is being absorbed by that chamber of gas. And you can actually mathematically describe it to this equation right here. So Beer's Law allows us, by looking at what the light should be and observing how it actually is, we can actually back out the composition of this gas that's doing the absorbing in the middle. So we can actually use light to figure out what molecules are present in many astrophysical sources. So for example, let's say we're an astronomer using a telescope. We're observing a yellow star. Well, that yellow star will emit yellow light, and then we'll observe it and it'll look yellow. Makes sense. But what happens if we put like a cloud of gas and dust between us and the star, like a nebula? Well, that big cloud of gas and dust will absorb that yellow light and actually cause it to slightly redden a little bit. So if we use Beer's Law, we can observe what a planet or not. So if we observe what an object does look like, in the case this star looks red, and we compare it to what it should look like, yellow, we can then use Beer's Law to determine the composition of the absorber. We can then figure out, for example, that this cloud actually has molecules in it. You can also apply this to exoplanets. So an exoplanet, a lot of them, just like the Earth, has a hot core, and that hot core actually emits light. And if we use a gaseous planet, like a Jupiter-sized planet, or a Jupiter-like planet, that warm core will emit light that then is escaping through its atmosphere. And the atmospheric layers are slightly cooler than this inner one. And that causes that light to go from yellow to red. So then astronomers at the other end of our telescopes can then say, hey, that planet has methane on it, just by directly adapting Beer's law to those measurements. Similarly, we can look at something like a Jupiter planet and look at how light is reflected off its surface. So in our own solar system, Jupiter takes the light from that yellow sun, and then it reflects it back to us slightly reddened. We can then, astronomers on the other end, can use Beer's law to figure out that that planet has clouds on its surface. So again, Beer's law allows us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. So literally, just by looking at light, we can figure out what things are made of hundreds of light years away. So here's some actual data for some exoplanets. On this axis is about 7 last time I counted, and I'm too lazy to count again, exoplanets. On this axis, we've arranged them, and by me I mean Julien Rameau and the GPI team has labeled them in terms of hot on the top and relatively cool on the bottom. On the x-axis here are a variety of wavelengths. So what they've done is they've observed these exoplanets at multiple wavelengths of light. And what they're able to do is basically match this up with where other molecules are routinely predicted to absorb light. So water, for example, absorbs most strongly at these wavelengths. So if you see a bumper wiggle at these wavelengths, the planet likely has water on its surface. These wavelengths correspond to methane. And this wavelength passband out here corresponds to carbon monoxide. So just by looking at these spectra, how the light varies with wavelength, you can actually figure out the composition of these planets. So some of you eagle eye observers out there might have noticed these gaps in the data. Well, this data was actually taken from the ground, the surface of the Earth. And these passbands right here, these red zones, are actually where the Earth gets in the way, where stupid things like water actually absorb so much light we can't see through those passbands. So if you can't observe them on the ground, what do? Well, you go into space. This is why space observatories are so important. It allows us to observe outside the Earth's atmosphere and to see at wavelengths that are normally obscured partially or even fully by the Earth's atmosphere. So one mission that you've probably all heard about is the Hubble Space Telescope. Hubble actually has been observing water absorption, and it's observed that about 50 exoplanets, I believe, or so. And it's able to access that passband because it's able to fly outside the Earth's atmosphere and actually look for water. So in other words, the Earth's atmosphere can actually prevent us from observing and monitoring molecules that we want to see, because those very same molecules get in the way on the Earth's atmosphere. And that's one of the reasons we're so very excited about the launch of James Webb. James Webb is the successor to the Hubble Space Telescope. It also expands upon the Hubble Space Telescope's wavelength coverage. And in addition, it's just purely a giant telescope, folks. Hubble's about a 2.5 meter telescope. This is about a 6 meter telescope, so about 20 feet across. This purple thing on the bottom is its solar shield. It's the size of a tennis court. This telescope is such a giant beast that they actually have to fold it in up on itself like origami to fit inside the rocket nose cone fairing so it can be launched out into space. And then once it gets out into orbit, it actually slowly unfolds for many, many days to get its full size. I was actually very lucky enough to see this when I was out here in LA for testing as well. And this sort of our reason for why we're so excited about space-based telescopes is why we're also very excited about the upcoming launch within the next 5 years, likely 2026, I have to update that date, sorry, of the Roman Space Telescope. So the Nancy Grace Roman Space Telescope was named after Nancy Grace Roman. She was the mother of the Hubble Space Telescope. She was one of the major forces to getting actually Hubble launched by NASA. And this telescope is really cool because it actually has 100 times the field of view. So what Hubble would take 100 observations to make, Roman can do it in one single shot. And one of the instruments that's on board is the Coronagraph. And that actually does direct imaging of exoplanets. I'm really excited to be working on the Roman Coronagraph because it really is a stepping stone or a technology demonstration to get us from where we are to where we want to be. Currently, direct imaging is typically done by large ground-based telescopes. And these telescopes are routinely or typically seeing planets that are far from their host star and planets that are very young and therefore still radiating light left over from when they formed. But where we want to be eventually is we want to find Earth-like planets. We want to find planets that are small, that are radiating or reflecting less light, that are cooler, that are also closer to their host star. And Roman allows us to have that stepping stone to get there, because Roman will allow us to observe closer in, cooler planets, also maybe potentially smaller planets, but definitely planets that are true Jupiter analogs, which will be pretty incredible. So actually Jupiter-sized planets and Jupiter-sized orbits at Jupiter temperatures. And that technology and all those lessons learned will be directly applied to future missions that will be observing that holy grail, Earth-sized planets orbiting around sun-like stars. So given all these great things, why we even bother with the ground? You know, space-based telescopes, they're not limited by Earth absorption. They're minimally impacted by sunlight, but they're very limited both in available time and wavelength space. Space-based telescopes are truly a very precious resource that the entire community is scrambling basically to apply for time for. Ground-based telescopes, on the other hand, there's numerous platforms and instrumentation. There's a ton of telescopes across the world, but you do have to deal with things like the Earth's atmosphere. So with that in mind, I'm actually the JPL commissioning lead of a new instrument that's being tested and commissioned right now at the Palomar Observatory out here in Southern California called NESI, the New Mexico Exoplanet Spectroscopic Survey Instrument. And there's the 5-meter, 200-inch Hale telescope. It's a very historic telescope, but for about 50 years is the world's largest. And you know, this is a telescope that was built before exoplanets were even discovered. And it's pretty cool to be using such a historically significant telescope and a big telescope as well. And the major difference there is just our instrumentation, and that allows this telescope to see exoplanets. So let's get into a cool photo that I took the other day of Nessie. No, that's a mythical sea creature. Sorry, everyone. This is actually Nessie. That's the blue thing right here on its silver handling cart. Here's some of its hardware. I'm doing some testing, I think, in one of the labs at Palomar Observatory. And here's Nessie actually installed at the top of the telescope. And I can talk about this later if anyone has questions about it. But Nessie sits at the top of Palomar Observatory. It replaces its secondary mirror, giving a nice big field of view. And when we actually did our fit tests, myself as the commissioning lead went up there with my boss, Mark, and Mark is smiling at the camera. He's actually laughing at me, guys, because I'm definitely afraid of heights, and I'm about 100 feet up in the air working on this instrument. So he's really enjoying my pain, but at least I got a really cool photo and kind of a weird selfie out of it as well. But yeah, we've been, for the last year or two, been making really nice transit observations of transiting exoplanets, and hopefully very soon we'll be directly contributing to characterizing the atmospheres of these planets. All right, so we've been talking a lot about how to find planets, how we can use Beer's law to look into its atmosphere, to determine the composition of these planets, to see if it has molecules like water, carbon dioxide, methane, things that life needs on the Earth to survive. Now we have to take the next step. We have to find life on that surface. Just because a planet could support life doesn't guarantee that life exists on its surface. So let's do a thought experiment. How do we find life? What are the things we would look for? Well, let's pretend we launch a satellite into space, and while it's zooming out into the outer parts of the solar system, we have it turn back and look at the Earth. We can have it analyze the reflected light from the planet and use Beer's law to look and see if the planet has an atmosphere, if it has oxygen that could be made by algae that makes ozone, We could look for liquid water, or we could look for signs of biological activity like cow farts, right? But we have to rule out all other explanations. We're currently finding water, we're currently finding methane, we're finding a bunch of molecules on these planets. But the majority of these planets are large planets that are very, very close to their host stars, called hot Jupiters, and they're inhospitable to life. So you really have to rule out all other explanations. Or alternatively, you can just send messages to talk to aliens directly. So Voyager 1 and 2, they were actually built at JPL. They were launched in the mid 70s and they did this grand tour of the solar system. And they have these golden records on board. And what these have is they're actually recordings of Earth sounds and also a bunch of different languages saying greetings to people. And they also have pictures of Earth as well. And this golden record is so that an alien civilization, if they find Voyager 1 and 2, they can then be instructed on how to make their phonograph, how to project the picture correctly on their TV screen, and then where to find us by looking at a bunch of pulsars. It's pretty cool if you ask me. Alternatively, you can also talk to aliens by sending them messages. Back in the day, in the mid 70s as well, they used Arecibo. Rest in peace, unfortunately. This was at time the world's largest radio telescope. It was so big that it was actually nestled in a valley between mountains. And what they did is they beamed this message out to a globular cluster called M13, where they saw tons of stars, so they potentially had tons of planets. And they sent out this message right here on the right. So you can probably figure out the red thing is, that's a person. At the top in white is instructing aliens, hey, we're not too dumb. We know how to count. We know about molecules. This double helix thing, we know about DNA. Here's how we sent our message. We sent to this radio telescope, and here's where we live. So there's the sun, Mercury, Venus, Earth elevated, because that's where it sent the message. Mars, Jupiter, Saturn, Uranus, Neptune. And guys, this was the 70s when they didn't know any better. They have Pluto on here, but we know better today. Pluto is not a planet. So basically it's saying to aliens, hey, we're this intelligent race. Here's where we live. Come and enslave us. Hopefully we will learn from Independence Day and cryogenically freeze Will Smith to help us battle the alien onslaught. Alternatively, we can also send messages to aliens. So for example, back in 2008, there's a social media network called Bebo. Here it's big in Europe. They actually beamed some messages to the star system called Gliese 581. And planets C and D are potentially in the habitable zone around that star. So messages will be arriving in just a few years in 2029. And if there are aliens there and they immediately reply, we'll be hearing from them in 2049. So these efforts are still ongoing, which is pretty cool. So the question is, where are we now? So unfortunately, despite what the History Channel and Ancient Aliens might tell you, we have yet to make any conclusive detection of extraterrestrial life. And the question is why? Why haven't we found aliens? Planets are everywhere. There's at least as many planets as there are stars in the sky. Why haven't we found life out there? Well, maybe our technology isn't good enough. It wasn't until the advent of digital cameras in the 90s that we had the technology necessary to actually see the signal of exoplanets. And once we knew how to look, when to look, we could then apply those, and we started finding planets everywhere. Alternatively, maybe we just haven't found them yet. Maybe they've been talking to us on this patch of the sky. We've only been looking over here. One great analogy that I really love, which is taken from Contact actually, is that if we were to take the known universe and shrink it down into the size of the Earth's oceans, while we think we know a ton about everything, we have yet only really explored the equivalent of a cup of water. So there's still much more out there that we have yet to explore, discover, and understand. Or maybe alternatively, maybe we are all just alone, and maybe life really is that unique and it only exists on Earth. But to avoid leaving you on a depressing note, today we are actually standing at a really cool time to be part of exoplanet science. And I've actually, over the course of my own career, been able to sort of experience and watch it grow from its very beginnings, from when the first planet was discovered in the mid-90s to today. We have this amazing foundation given to us by ground-based telescopes, by the Hubble Space Telescope. Spitzer's another mission that's been doing excellent exoplanet work before it was retired about a year or two ago. Kepler and TESS are planet hunting missions. The James Webb Space Telescope is the successor to Hubble and will really greatly expand our knowledge about exoplanets. And then the Nancy Grace Roman Space Telescope with the Coronagraph instrument will allow us to observe via direct imaging other worlds. And this is all great because these are giving us so much foundational knowledge that we can use for the next generation of missions. So right now, astronomers are getting together and are releasing, hopefully in the next week or two, a report about the direction that the field should be going on in the next 10 years. There are 4 flagship missions that have been proposed to this committee. 3 of them are LUVOIR, HABEX, and the Origins Space Telescope, or OST. And these 3 missions have all been explicitly designed to find life or search for life on exoplanets. So, and these are all launching hopefully as soon as the 2030s or 2040s. So perhaps within the next decade or so, we'd be able to finally answer that age-old question of, are we alone in the universe? So with that, thank you so much for your time. I really appreciate it, and I'm happy to take any questions.
All right, thank you very much. We've got some good questions going here. If we have any more, please add to this as we go. And let's get started right off. So Darian asked, and he modified his question, but maybe we can make this more general too. He said, originally he said using the transit method, and then he asked, meant radial velocity, but maybe you could deal with both. How accurate is the ability to determine the mass of an exoplanet? Do you know of a good reference or publicly available software that explains the math and physics required to measure the mass of exoplanets?
Yeah, that's a great question. And it honestly depends, unfortunately. So it depends on the brightness of your host star and the size of your planet. The bigger the planet, the bigger the wobble on this host star. So the bigger the signal, the easier it is to see. The brighter the host star, the better your measurement quality will be as well. So there's unfortunately not like here's the exact answer, because it does vary from target to target, from host star to host star and planet to planet. But effectively, at the end of the day, what you're doing is you're measuring that wobble of the star. And you can actually, it's almost as simple as fitting sine waves to that signal. And the amplitude of that sine wave gives you constraints on the mass of the planet. And then the periodicity or the frequency of that sine wave tells you how quickly that planet orbits around that star. So as far as references, there's a ton. What I recommend you do, though, is you go online and you Google NASA 5 ways to find an exoplanet or 5 ways to discover an exoplanet. They actually have some really nice hands-on animations and descriptions on how this actually works. So that's a great resource as well.
All right. There was a little bit of a discussion in the chat having to do with cameras. And so Gregory posed the question, what type of camera is required? And he was thinking, and I'm not sure what the acronym, ZWO, ATIC, etc. And then there were some questions about the chips as well.
Yeah, doesn't matter. Anything, as long as it collects the photons, that's all we care about at the end of the day. We're actually experimenting with some ZWO cameras right now. Also, I know Unistellar, for example, is using ZWO cameras, I believe, in their chipsets on their EV scope, or yes, EV scope. And basically, at the end of the day, they just care about measuring the light and collecting the photons. You could use a DSLR camera. You have to do some detrending of your array because of the Bayer array. We have people using CMOS cameras, CCDs. So really, it's anything and everything, honestly.
Are there any resources that people maybe could access so that they, or maybe that's on your Exoplanet Watch site, about recommendations and settings and things like that?
Yeah, we're actually developing that right now, and it should be up on our website hopefully in the next week or two. We do have other resources with links elsewhere. For example, Dennis Conti of the AAVSO has a really nice sort of how-to guide, and there's tons of YouTube videos. But alternatively, you are more than welcome to sign up for our project, join our Slack channel. It's how we all interact and communicate with each other. And we have a ton of amateur astronomers on there that are really knowledgeable, and a lot more knowledgeable than I am, and they can definitely recommend some different setups for various budgets as well. Right. Oh, and thank you for the correction, Philip. Appreciate it.
Okay, Randall asked a question. When you talked about Beer's law, you started by stating, if we know what the light from the star should look like, how do you know that?
Yeah, that's a great question. This was always something that confused me as an undergrad all the time, is how do you know what it looks like or should look like if you're looking at it, what it does look like. So you can actually sort of figure out by looking at a star, you can say, oh, that star is like a G-type star, but we're noticing that these wavelengths are blocked out or that the light is just shifted red or blue. So basically you have to look at the entire picture to figure out what the star should be looking like. And then that way you can sort of infer what sort of information is missing. Like for Beer's law, if you're observing a G-type star, like a sun-like star, that should be absorbing, or sorry, emitting yellow light. You put that gas cloud in front, that gas cloud is actually going to block out or absorb light at various wavelengths according to the molecules that are in the gas cloud. So you can basically see these, you can see the spectrum of the star, and then you'll see these little lines that dip down that are indicating absorption by that gas cloud. And you can actually look up that pattern and then figure out what molecules are doing the absorbing.
Right. So Marco's asked a question, fairly specific here. Any news about the Trappist system? A few years ago, there was a lot of noise and it was in the news a lot.
Yeah, so the Trappist system, I actually have a little quick slide about that. 1 second. Let me find that in my giant slide deck. Right here, I'll share my screen. So the Trappist system is very exciting because it's a multi-planet system. It has 7 planets that are all roughly Earth-sized planets orbiting around a small star. And these are all Earth-sized, but planets E, F, and G actually might be in the habitable zone of their host star. So these 3 planets actually might have conditions conducive to life. These planets have actually been observed by the Hubble Space Telescope, and Hubble has found evidence of water potentially in the atmosphere of all 3 of these planets. And as far as I'm aware, James Webb will be observing the system as well. I believe that's still the case. So stay tuned. Once James Webb launches in December and goes through a bunch of commissioning over the next few months, perhaps within the next year, you might, or 2, might hear about new observations with this new observatory of the TRAPPIST-1 system.
All right, and I think you just answered Scott's question. He says, when will JWST come online? And so maybe a year from now.
Launches in December, and then I forget the exact timeline, but it has a bunch of commissioning steps. So it takes time to get out from the Earth out to its final orbit, and then it takes time to unfurl. Then you have to check out all the instruments, make sure everything survived, everything's operating correctly and sufficiently, and then it can start doing those observations. I believe observations are slated for next fall for the science program, but observations will likely be happening before that for commissioning of the instrument to make sure things are working correctly.
All right. Okay, we got a couple more questions here. So Stephen asks, how well does the radial velocity detection method work for orbits of planets that are perpendicular to our line of sight?
And you're absolutely right, Stephen, it doesn't work at all. So if the planet is orbiting perpendicular to our line of sight, the star will be moving up-down direction, and we won't see the Doppler shift of that light. So the radial velocity method and the transit method both rely upon that geometry. The planet has to be orbiting within that plane that is parallel to our line of sight. So you can either see the planet block out the light of the host star, or we can see the wobble of the star as the planet tugs on its host star. So you're absolutely right. We're missing, or we're not able to detect some planets because their orbits are perpendicular to our line of sight, and they don't cause either a transit or a radial velocity wiggle.
Okay, we've got, I think we've got time for just a couple more questions here. And these are a little more philosophical. I like this one. Mustafa asks, finding life in faraway places means that the life and the life on Earth will not be simultaneously contemporary. What we find will really be from the distant past, right?
Potentially, I don't know. That's a great question. Whenever we look in space, the farther away we look, the more into the distance past we're looking. And that's just simply because light has a finite speed and it takes time for light to reach us. So for example, the light from the sun, it takes 8 minutes to reach us. So if the sun were to magically turn off, we wouldn't find out about it for 8 whole minutes. Whereas the nearest star to us is about 3 light years away. That's the closest star. It still takes light 3 years to reach us. So whenever we're observing the system, we're actually observing as it looked like 3 years ago. The planets that I'm studying, most of them are about a few hundreds of light years away. So I'm effectively looking at things that have already happened hundreds of years ago, which blows my mind. So if we're looking for signals or detections, you're absolutely correct. That's stuff that's already happened in the past, simply because that information hasn't reached us yet. That being said, there are some stars that are as old as the universe and as our galaxy. The sun and the earth are sort of middle-aged comparatively to the rest of the universe. So there could be potentially a civilization that formed on a planet around one of these older stars, and it's, you know, millions, if not billions of years older than our own. And that could be really cool to think about. You know, there might be this very technologically advanced civilization, or maybe they all got mad at each other and blew themselves up. Who knows? That's what makes the field so interesting. Hopefully it's not as depressing as the second option, though.
Okay, so we'll go for the last question here. And so Marcos says, will we find an Earth-like planet before we destroy the Earth? And my add-on to that is, if we do find one, what do you think that'll do as far as our attitudes and perspective about life here on Earth?
Yeah, I really hope so, Marcus. That would be great to find an Earth-like planet before we destroy the Earth. I'm trying to be optimistic here on this random Thursday night, drinking my soda water. But ask me again after I've had a beer, and that might change as well. But yeah, I really do hope so. I've always been interested in the sci-fi person myself, and the question of are we alone in the universe is really one of those fundamental questions that's really going to change our entire history. Up until now, you know, it's only been us on this one planet. And when we discover life, hopefully in the next decade or two, it could be that soon, which is incredible. That is going to just completely shift our perspective on everything and anything. And it's just going to completely change our history. So it's going to be incredible to live through. It's kind of interesting to live through COVID times and the pandemic and all the history that we've been through the last few years. And hopefully this will be something good that we can look forward to happening in the next few decades.
All right. Well, thank you so much. That's all for tonight. Thank you, Rob, for joining us this evening. And thank you, everyone, for tuning in. Join us for our next webinar on Monday, November 22, when Erica Blumenfeld from NASA's Johnson Space Center will share with us stories about the astromaterials. And so, you know, maybe someday we'll have astromaterials from beyond the solar system. And so these are materials from other objects within the solar system that NASA has archived, and how they have inspired both researchers and the public. You can find an archive of these webinars on the NASA Night Sky Network website in the Outreach Resources section, and each webinar's page also features some additional links to resources. And I believe that Exoplanet Watch is in there. You can also find these webinars on the Night Sky Network YouTube channel. So keep looking up, and we will see you next month. Good night, everyone.
Yeah, thank you guys for having me. Really, really appreciate it. This was a blast.
Yeah, this is really, really great. So I learned a lot.
One of my favorite presentations I've ever seen. Thank you.
Oh, thanks, guys. Really appreciate it. That means a lot.
You got a lot of props in the chat. Thanks.
Oh, great.
Oh, gosh, yes. So, well, I look forward to, actually, we've still got a few people on here. I would love it if those of you that are still on here, if you have participated